Okay, today we're going to talk about some the SI units, the metric system, and how we do calculations with our measurements. But kind of to review, the matter is anything that takes up space and has mass. And mass is a unit or a measure of the quantity of matter. And for the SI units, SI is the System International. So before they had these SI units, scientists all over the world were using different units, and when they published results, I don't know how much you used, because you used, I don't even know a different unit, pounds, but they had even stranger units even. So they came up with this System International that everyone would be using these, and that would be based on the metric system. And the SI unit for mass is the kilogram, not the gram. So it's the kilogram. When we're in physics, everything that we measure has to be in kilograms. When we do calculations, we can use some grams and it'll be okay. But remember, 1 kilogram is equal to 1,000 grams. And then weight is the force that gravity exerts on the object. So it all depends on what the acceleration due to gravity is. And so weight is equal to the gravity times mass. So on Earth, C is 1, and it's about 0.1 on Moon. So you can see that the gravity, force due to gravity on the Moon is about 1/10 of what it is on the Earth. So the weight will change. I don't know why they have, but the mass doesn't change. Okay, mass does not change, the weight will change. So here's our SI units as the length, and this is in meters. Mass is kilograms times second, and temperature is Kelvin. Those are the units that we will be using. We'll use degrees Celsius a lot for temperature until we get to gases, and when we look at gases, we have to be in Kelvin. And the prefixes with the SI units are here. We need to know from being able to change from kilo to milli by yourself and anything in between there. And they don't list them all here. If we, from largest, it's K. And I forget the saying. Some people have the saying that goes with this, like King Henry's dog. I don't remember. Does anyone have that? No? No one learned it that way? Well, this is the kilo, like the base is whatever unit, like if you're in volume or mass. So let's say we're in volumes. So we're going to use liters. So kiloliter, hectoliter, decaliter, a liter, and then a deciliter, centiliter, and milliliter. Those are the unit. So we have kilo. We don't have, this would be hecto, and this is deca, base, and then we have these three written down here. So from here to here is what we need to do. No. The base, so it could be grams, meters, liters. They just call that the base. And so everything's based on the power of 10, so it's really easy to convert from one to another. You divide by 10 or 100 or 1,000, and when you do that, all you have to do is move the decimal point, right? And so if we're converting from kilograms to milligrams, if we're at kilograms, you can use this little thing if you want to change it. just disconnected. I don't know what happened. Is it working?
Oh, it changed lines.
Whoa. There. So let's say we're going to kilograms to milligrams. We can just count over. We move our decimal to the right 1, 2, 3, 4, 5, 6 times. You can use that. Or if you have a kilogram, we're going to do some dimensional. Actually, when we get to the dimensional analysis, I'll show you that later. I think that's tomorrow. Okay, volume. The SI is a derived unit. Derived units is when you take any of those SI units and combine them with another. So volume, you're taking a length times a length times a length. So you get a derived unit of a cubic meter. We usually don't use volumes as big as a cubic meter. Okay, that's a big volume. So we use, we are basing everything based on a milliliter, and 1 milliliter is equal to 1 centimeters cubed. On like, does anyone watch House or anything like that? It's there. Yep, when you give them like 2 cc's, it's cubic centimeter. So they're talking about 2 milliliters. Same thing. Oh, does anyone need to copy anything down for that? Okay. Density is also a derived unit because we're taking a mass divided by volume. So our derived unit would be, you could use centimeters cubed, or milliliters. These are all appropriate, okay units, depending on what your measurements are in and depending on what the question asks for. But our equation, we want to use this equation right here. Density is equal to mass over volume. So if a piece of a platinum metal with a density of 21.5 grams centimeters cubed has a volume of 4.49 centimeters cubed, what's its mass? Our equation is D equals M over V, right? What's our density? One thing we do need to check, are the units over here the same as this unit so that it's able to cancel out? And it is in this case. If it weren't, we'd have to change units for one of them. So to solve, do we multiply or divide by 4.49? Multiply. And which is why when we have, we're going to have a centimeters cubed multiplied by this, the centimeters cubed end up canceling each other out. So we get, the answer you said was 90 something?
96.5.
I'm going to put 5.4 grams. Don't forget your units. I do take off points if you don't put units. Grams. Centimeters cubed canceled out, right? So we're left with grams.
So if that wasn't centimeters cubed,
You'd have to change,
something else. So how would you do that?
you'd have to change the units. Yep.
So you just move the decimal, use that little chart.
Yeah, or you, if one of them is a milliliter, 1 milliliter is equal to 1 centimeter cubed. Yeah. Oh, it's going to go through the whole answer. How do we get that? Yes. Okay, temperature. Here's the three temperature scales, the Kelvin, Celsius, and Fahrenheit. We will not be using Fahrenheit, but we do need to know how to convert. If you measure something in Fahrenheit, how do you get it into Celsius? It shows you some of the points, like the boiling point of water is a common temperature, 100 degrees Celsius, 212 Fahrenheit. Body temperature is 98.6 Fahrenheit, but that's about 37 degrees Celsius. Room temperature, 25 degrees Celsius, 77 degrees Fahrenheit, and then freezing point of water. Okay, the Kelvin scale starts at 0, and then it goes up to the, and there's no limit to how high it can go. What do you guys know what 0 Kelvin is called? Absolute zero. And we will watch a video, I think it's next semester, about absolute zero, like tomorrow. So. Okay, so to change Kelvin in Celsius, you take the degrees Celsius and you add 273. Does your book actually use the 0.15? It does. Okay, 273.15. And so there gives you a couple equalities there. Thank you. Okay, to change Celsius into degrees Fahrenheit, you take 9/5, which is 1.8. So if you want to use the number 1.8 instead, that's fine. I like 1.8 instead of 9/5. 1.8 times the degrees Celsius, and then you add 32. So it gives you some equivalent points. Oh, shoot. Let me put it. What if you wanted to change Fahrenheit into Celsius? What would you do? We'd have to subtract the 32 over first. Yep, and then multiply all that by 5/9. Okay, now really, I don't have those equations memorized, but I know how to figure it out without seeing the equation, because if you know that the boiling point of water, the two temperatures, I use 1.8, so I either know you have to multiply by 1.8 or divide by 1.8, and you either add or subtract 32. So then if I just usually take one of the numbers, so my Celsius number, try to get it to 212, using those two things, and then figure it out from there. But if you like to memorize equations, you do need to know how to do this. Okay? Memorizing the equation is optional. You have to be able to convert it, though. Yeah. Okay. So we're converting 172.9 degrees Fahrenheit to Celsius. Gives us our equation here. I think it's going to rearrange it like what we just did. There we go. So we'll take 172.9 and subtract 32 first, and then multiply by 5/9. Yeah. You should get 78.3. Yes? Make sure you can get that. Everyone getting 78.3? Okay. Oops. Do I need to go back? I thought there was some. Yes? We'll talk about that when you how you round. What? That it's all based on significant digits, significant figures. Now can I change it? Okay. Solder is an alloy made of tin and lead that's used in electronic circuits. A certain solder has a melting point of 224 degrees Celsius. What's its melting point in Fahrenheit? Is it 9/5 times degrees Celsius plus 32? Is that right? No? Yeah? Okay. Right, it should be very high. Fahrenheit's usually higher than Celsius, so. $435.2. Yep. Like it. The other thing is if you convert to Kelvin, you don't put degrees Kelvin, it's just Kelvin. Okay? Helium's lowest boiling point of all the elements at negative 452 degrees Fahrenheit. Convert that into Celsius. So it's 5/9 times it's Fahrenheit. Oops. You should get 233.3. No, multiply by 5/9.
That's what I did.
Okay, I got
Yeah, you're supposed to subtract 32.
Yeah.
I got,
Oh, I forgot the negative sign. Huh.
yeah, I got negative 219.
200.
I don't even know.
I have 200, negative 268.9.
that's what I have.
Okay.
I hate that. I hate technology.
Okay, so you take the negative 452, 52, subtract 32, which equals, that's negative 484. And then you multiply by 5/9.
I got negative 434.
I still get negative 268 and 8/9 this time, but let me see how you do it.
What is this?
Divide by 1.8. If you use the 1.8, divide by 1.8.
So multiply by 5 divided by 9 still.
Yes, if you use 5/9, then you'd multiply. But if you use the 1.8, so when I use 1.8, I divide by 1.8.
Did I do something? What did I do wrong?
Oh, I was using 425 instead of 452. That's why.
I'll bet you need parentheses here. No. Oh, because it's taking 32 times 5/9 and then subtracting that from 452. So you need to put parentheses around the 452 minus 32 and then multiply that by 5/9. Because remember the order of operations, it's going to multiply first.
Minus 32. Oh, wait. Parentheses. Parentheses. Minus 32
Times 5/9.
I just do accept it.
Yeah, oh, you forgot your negative sign.
Oh. I was
Do you have insert?
I have no clue. I just got the calculator. I usually use the Casio, and it's usually a lot nicer.
There you go. If you second insert that, there you go.
Thank you.
Did everyone get that then? That answer? Okay. Scientific notation. I'm sure most of you are familiar with scientific notation, where you're moving the decimal point so that the number is between 1 and 10. And then you multiply by 10 to the number of spaces you move to the decimal. So if you have, this is what it's going to look like. N is the number between 1 and 10 times 10 to the power of however many decimal places you have. Just remember, if the original number is really big, you're going to have a positive exponent. If it's really small, you have a negative exponent. So if you have a positive exponent, you're moving the decimal back to the right to get to the original number. If it's a negative exponent, you move the decimal place to the left to get to the original number. Or if you like to think of, if you take the original number and to get it into scientific notation, you move the decimal to the left, then your exponent's going to be positive. If you had to move it to the right, then it's going to be negative. However you like to think of it. I always think of, if my number is really big, I have a positive exponent. If it's really small, like less than 0, then it's going to, or less than 1, then it's going to be a negative exponent. So 568.762 is what in scientific notation? You have to move the decimal so that it's between 1 and 10. I move the decimal over here, and then it's 5.68762 times 10 to the second, positive second, right? Moving the decimal left. Yes, yes, yes. There we go. No, you should not round that number. This number, we're going to move the decimal to the right. So as we're moving it to the right, we're going to have a negative exponent. So I count over 1, 2, 3, 4, 5, 6. 7.72 times 10 to the negative 6. This number is less than 1, so it's a negative exponent. So what would the first problem here be? What? Negative first, right? Yep. Second one? This one. To the negative 1, 2, 3, 4, 5, 6, 7. Yes. Okay, these two let's write out in their decimal form. So this would be, we're moving the decimal which direction? To the left, right? 1, 2, 3, 4, 5. So we have point 1, 2, 3, 4. Yep, 4 zeros in front. Remember, if it's a negative exponent, that means that number must have been less than 1. So small. If it's a negative exponent and you're moving it back out to decimal, negative means you're moving it to the left. Positive would be to the right, so we should have 603 with 4 zeros behind it. 6,030,000. Questions on scientific notation? Okay, and last thing today, significant digits. Significant figures are important because, let me, get all that up there. It's all based on measurements. So everything that we are measuring, we have to estimate that last digit. So let's say that we're measuring the length of something, and that length falls in between two of the markings on our rulers. You always need to put an estimate, whether it's add a 5 at the end because it was halfway in between, or if it's closer to one or the other, 7 or 8. But you always have to put that estimate. If it's right on the marking, you still need to add a 0 at the end to show that it was directly on that marking. And so when we were looking at all those digits that we actually measured, and those are considered significant digits, significant figures. And when we see numbers in measurements, we do have to consider their significant digits when we go and calculate numbers from those measurements. So we need to know how to count significant digits first. So we have some rules. Any digit that's not 0 is always significant and counted as a significant digit. The zeros are where it gets tricky. So zeros that are between two significant figures are significant. I want to just see what I have on the next slide. No, okay. I'm going to call these captive zeros. Those zeros are being held captive between two non-zero numbers. So example, 606, that 0 is being held captive. So we do count that 0 as significant, and it has 3 significant figures. Zeros to the left of the first non-zero digits are not significant. I'm going to call those leading zeros. So any leading 0 is not significant. So this 0.08, those two zeros come before any other number, are not significant, so we only count the 8 as the significant digit. If a number is greater than 1, then all zeros to the right of the decimal point are significant. And if it's less than 1, then zeros that are at the end and in the middle of the number are significant. I'm going to combine these two and call them both trailing zeros. And the rule with trailing zeros is that trailing zeros are always significant if there's a decimal point. If there's a decimal point in that number, trailing zeros are significant. So I'm going to put trailing zeros are significant if the decimal is present. So here, these 3 zeros are leading zeros. They're never significant, so we don't count these as significant figures. This is a trailing 0. There is a decimal point in this number, so the trailing 0 is significant. So we have a total of 3. So hopefully by just remembering these 3 captive zeros, leading zeros, and trailing zeros, and the rules for them, that'll help make it a little easier. So let's see what we got here. Actually, I think you need your clicker for this. So when you go grab your clicker quick, yeah. With my writing on it too?
No, I just
Oh, okay. Okay, so how many significant figures? I think, yeah, there's numbers on there. How many significant figures are in each of these measurements? So 24 milliliters. How many significant figures are there? And number one must be Sam, and he's gone. The answer is it going to show? 2, yes. Non-zero numbers are always significant. So 2. Okay, how about 3001? And 4 is correct. Remember, those 2 zeros are called captive zeros. Captive zeros are always significant because it's between 2 non-zero numbers. .0320 meters cubed. And it is 3. Okay, these 2 zeros are called trailing or leading zeros. Leading zeros are never significant. This is a trailing zero. Is there a decimal in that number? Yes, so if there's a decimal, it is significant, so we have a total of 3. .4 times 10 to the 4th. I'm going to hand these out. These won't be due tomorrow, but you could start on them. No, because I don't think we'll get to all the notes for them. Okay. The answer is 2. Yes, 2. So let's write this one out. What if you wrote it out like that, if that's the actual number? Okay? You can't just add a decimal at the end. So even when I count this, these are trailing zeros, but there's no decimal. So it's still, you don't count the trailing zeros if there's no decimal, so it's still just 2. Actually, hold on. Still my pen. Okay, this number. Who's number 4? Who is number? Oh, there we go. It is 2. Just like that last one, this 0 is a trailing 0. Is there decimal point in that number? No, so it is not significant. So we just count the 5 and the 6. That's 2. And I think we're going to stop there, because I don't think we'll have time to get through all this.